Hello. Today I'm going to talk to you about graph theory. This is a big topic, so pay attention. What exactly is graph theory? Well, it's an important concept in computer science and also mathematics that generally is about how you can link different pieces of data together in a meaningful way. So it's sort of like a web. Now, when you think of the word graph, or graphs as you might have learned them in school, you probably think of pie graphs, bar graphs, line graphs, and so on from math class. In computer science, graph theory is probably most similar to line graphs, but it's not exactly the same, and I'll show you with an example in a second. Here, for our purposes, this is a graph here on the side. Our definition of the graph that we're going to use is a finite number of vertices that are each connected by a number of edges. In formal terms, you can define a graph as G, which is equal to the vertices and edges. Note that graphs can have different properties, that the edges could also be directional, meaning that they can only travel one way, as opposed to the example I show you above, which does not show any direction, therefore you can travel along them in any way. Now you're probably thinking, why? Well, why do we use graph theory? Why is it so important? Well, consider some different problems that in the real world that use different points that connect to each other. Suppose you wanted to travel to 10 cities as quickly as possible without seeing the same city twice. What if you had to connect a huge network of people as efficiently as possible? Graph theory is considered to be of high importance for research into algorithms to answer such questions. There is one well-known question about the traveling salesman, such that there's a map given of the salesman route, that of all the cities that the salesman has to follow and go to, and the salesman wants to be efficient about his travels and travel to them as quickly as possible without repeating the same city twice. You can look that up on your own time. Now I'm going to give you some different terms for used in graph theory. Degree means, well, if you have a degree of a vertex, that means that's the number of edges that connect to that vertex. Adjacent means that a vertex would be adjacent to another vertex if they are connected directly by one edge. An edge would be adjacent to another edge if they are connected by one vertex in between them. A general theorem for you is that the sum of all the degrees for all the vertices of a graph is equal to 2 times the number of all the edges. Interesting, which is useful for some calculations that you might do with graph theory. Here's some more terms. If a graph is undirected and there are no self-loops within it, which means that the edges that attach to the same, there are no edges that attach to the same vertex from both sides, and there are no multiple edges, then the number of edges is always less than or equal to the number of vertices times the number of vertices subtract 1 divided by 2. Alright. A simple path is a path from one vertex to another containing no vertex that repeats. A cycle is a path that starts and ends in the same vertex. A subgraph is a graph with some of the same edges and vertices of a larger graph. Okay, there's more. Trees. We've talked about trees in another video, but I'll go over here. Trees are technically types of graphs, where all the vertices are connected to the graph, and there exist no cycles in the graph. A forest is a collection of trees. A complete graph is a graph such that every vertex is connected to every other vertex directly. A property of complete graphs is that the number of edges is equal to the number of vertices times the number of vertices subtract 1 divided by 2. And a spanning tree is a subgraph that is a tree that contains all the same vertices. Okay. Well, graph theory, as you can tell, is a very large, complicated topic. We've just covered some of the basic things over today, just some of the basic terms and concepts about it. And to go over everything would take multiple videos, and I don't think we have enough space on YouTube to fit it all in one video. In universities and colleges across North America, you can find full-length classes that are dedicated only to graph theory, which should tell you about how large this topic is. What we've seen so far is just a basic understanding. I highly recommend that you should take a class to learn more about the theory of graphs and the applications for it. But now the fun part. Now that we know more or less what graphs are, how do we implement them when we program? Well, I'm going to show you. There are two main ways to program a graph. The first I'm going to show you is called an adjacency list. This means you would have an array of linked lists, each list representing all the vertices connected to the vertex in the graph. And the elements in the list would be all the other vertices connected to that particular vertex. As you can see from this example here, the first vertex I have is A, which is connected to B and C, which I have in the list. I have edges. The next vertex is B, which is connected to A and C in the list. And you get the idea. Okay, second way of representing graphs is in the adjacency matrix. If you know what a matrix is from math classes, you probably know that it's basically a table. And in programming, it would be a two-dimensional array representing a matrix that stores 0 in vertex I if vertex I and j are not connected, or 1 if they are connected. And none you can, it would take some representation of that anyway. You can notice if you look at the diagonal line here that the matrix seems to be symmetric along that diagonal line, which is an interesting property which might help you program a more efficient algorithm for finding what connects to what. Now, there are some different algorithms you can use to in computer programming. There's a algorithm called breadth first search to find all the vertices in a graph. Because if you were to try to find all the vertices in a graph, you can imagine, well, they're not in any particular order. So how would you, if you go from one vertex to another one, how do you know that you have to go back and you have to somehow find them all without getting lost? Anyway, this algorithm, what it does, it constructs a tree with all the vertices, starting with a vertex that you choose to start with. And it also starts with giving all the vertices a white label, or a white color, or some other way to represent that. Starting with the first vertex, you enqueue it. That means you create a queue, add it to a queue, and that if there's a vertex in the queue, you turn it to gray instead of white. Now you check for all the vertices that are connected to that one vertex, and you enqueue them into the list, and also turn them gray. When you've found all the vertices connected to the first one that you found, then you dequeue the first vertex from the list, and you also turn it black. And then you repeat with the next vertex in the queue that you created. Now, if you continue this pattern again and again until you eventually dequeue everything in the list, you'll be done. Also, if you find connected vertices that are not white, that means you've already found them already. Then you do not add them to the list because you don't want to repeat yourself and go do this indefinitely. Here's a basic pseudocode for it, to give you a general idea of it. As you can see, I enqueue with a starting vertex after giving them a color white, all of them color white. I also would give them a distance. I can record the the distance from each vertex from the original one. That's optional. Okay, moving on. Another algorithm is called the depth first search. Again, you start at a vertex of your choice, and you mark it as visited. Now, instead of sort of checking all the vertices connected to that one, you just check for one vertex connected to the first. And if it's not been visited yet, then you make that the current vertex, and mark that also as visited. And now you continue this again with that current vertex, and you check for another connected vertex, and you continue until all the connected vertices are visited, at which point you will go back to the last current vertex you had, and you'll keep going back and back until you eventually go back to the very first vertex you found. And yeah, that's it. Here's a pseudocode for it. It's not written directly in Java like the first one was, but it's that doesn't seem too difficult. Sorry, here when I say call DFS, I mean depth first search. That means I'm calling upon the same method again. Okay. Now another topic is a minimum spanning tree. A weighted graph, if a graph is weighted, that means that it contains numbers that represent weights for the edges of the graph. A logical application of this, you can imagine a shortest path algorithm that also considers the distance between two vertices, as opposed to the number of vertices in between. A minimum spanning tree contains all the vertices of a graph, with the minimum weight of the edges connecting them. How would we find such a tree? Well, there's an algorithm by a man named Prim, who helps define a minimum spanning tree. And here it is. Okay, here's another question for you. Suppose you want to find the shortest path between two vertices. Well, this is an important question, obviously. And there is an algorithm by Dijkstra, I hope I pronounced that right, that helps find the shortest path for each of the individual vertices all together, and it stores the distance for each vertex. And here it is. There's actually two different methods here at work, but you can study them later. Now, I've showed you a bunch of algorithms. Are these the only algorithms for these types of problems? Well, no, of course not. Others exist, and others are continually being developed and found and researched. The graph theory is a really big topic. It's a vast field in computer science and mathematics. And so I highly recommend to pursue this in further learning, practice, and study to best understand it. It might be complicated, it might be large, but it is important, and you might find out it's worth your time. Well, thank you for your time, and I hope you learned something. Thank you for watching.